Good afternoon, AP Statistics students. This is Mr. Tyke, and I got this new fancy writing pad, and this is going to be great. So, which ones are we doing? I'm going to do chapter 20, number 7. Then I'll do chapter 21, number 23, and then finally chapter 22, number 23. Whew, this is great. Okay, starting it off. Number 7 in chapter 20. Okay, here we go. A friend of yours claims that when he tosses a coin, he can control the outcome. You are skeptical and want him to prove it. He tosses the coin, you call heads, it's tails, you try again, and you lose again. So in other words, it's coin toss, but you want to know if he's making you lose, or if he's doing something to make it unfair. Okay, so A, do 2 losses in a row convince you that he really can control the loss? Well, 2 losses in a row, if we're only talking about 2 coin flips, we're only talking about these 4 possible outcomes. And the probability of any one of them is 0.25. So you're not going to get much, that's the highest p-value that you could possibly get is 0.25 in a significance test. 0.25 isn't going to, change anybody's mind, so 2 coin flips is not enough. Okay. B, you try a 3rd time and again you lose. What's the probability of losing 3 tosses in a row if the process is fair? Well, if the process is fair, then all possible outcomes from 1 coin toss, or from 3 tosses of coin, all the possible outcomes are equally likely. And there are, as you can see, 8 of them. And so the probability that, what is this, tails you lose? Well, it doesn't matter. The fact that you would lose means that one of these particular outcomes would have happened. So we're saying, what's the probability that any one of these particular outcomes would happen? So let's say you said heads, tails, tails, and it came out tails, heads, heads. Well, it doesn't really matter. The point is that whatever you said, it was the opposite of that. And there's one of these that's going to be the opposite of that. So the probability is 0.125. That by chance you lost 3 times, whether or not your friend is involved or not, right? Okay, so that again is not enough to convince us, everybody's gotten 3 in a row. That's not a big deal. Okay. C, would 3 losses in a row convince you that your friend cheats? No, we already said why. Okay, so part D. So I'm actually going to clear all this out because part D is where we actually have to do something mathy. So let's get this out of the way. So we're talking about D now. All right, let me just make sure that I'm recording. I get paranoid sometimes. There it is. Okay. All right, so how many times in a row would you have to lose in order to be pretty sure that this friend really can control the toss? So we're talking about a hypothesis test where the null hypothesis is that the probability is 0.5. In other words, the probability that your friend, you say heads, he tries really hard, he thinks of tails really hard. The fact that him doing that or whatever it is that he's doing will actually cause it to be the opposite of what you said. If he has no special skill and the coin is fair anyway, then this is the probability, right? But if he has if something unusual is going on, we can say that this is the alternate hypothesis. Now, as you can see, it's saying not equal to 0.5. In other words, I would be happy if you got an unusual, I would consider it weird if you were unusually successful. In other words, if your friend were controlling it one way or the other. The question specifies that how many times in a row would you have to lose, right? Which is one of the tails. So let's just draw what we're talking about here. Okay, so one of the tails. So I'm talking about a 2-tail significance test. So we've got some over here and some over here, right? And in the middle, since we're when we draw our distribution for a hypothesis test, we assume the null is true. So we say the center is 0.5, right? We'll get to the other part later. So, okay. So we're saying that you're losing, which means that your actual p-hat is really low, especially if you're losing every single time. Your p-hat's going to be 0. It's going to be all the way over here. Okay. So it looks like we're only looking at this tail, but the wording of the question also, it says, how many times in a row would you have to lose in order to be pretty sure that this friend can control the toss, right? Well, control just means that the probability will not be 0.5. That's what control means. So if your friend can control it, it would really be either tail. Now, the other reason I want to do two tail is it's more powerful. If I'm really going to believe that my friend has this special ability, you know, this better be good. This better be a really good significance test. So here's the part where we choose our alpha, right? Our alpha is, let's say, is 0.01, okay? Which means that we have to divide it in half for these individual parts here. In other words, the combined area of the two tails will be our alpha. So alpha is really the probability that by chance, you know, we are blown away by, it's really, okay, let's put it this way. One way to say it is the probability of a type 1 error, right? It's really the probability that we will reject the null hypothesis even if the null is, in fact, true. So, okay. Now, the reason I did all this, and you're going to see, I'm actually about to get rid of some of this stuff because I'm not actually going to go this route. And the reason is, you know, the wording of the question, they want to know how many trials would we have to do. So basically, if, I'm going to write this, if p hat equals 0, because we lose every single time, right, what does n equal if we also rejected h naught? In other words, okay, let me write it a different way. If p hat equals 0, and, well, actually, this gets kind of complicated. If we rejected h naught, we could technically reject h naught if p hat is 0 in any case, right? Because 0 is always going to be beyond, you know, within alpha, because 0 is like, well, I mean, you know, okay, fine, I'll take that back. 0 is not always within alpha. 0 is not always within alpha. Let's just put it this way. This gets kind of complicated, a little unnecessarily, and I think that that's why question 7 suggests that we justify our answer by calculating a probability and explaining what it means. So instead of grappling with these questions, which are interesting, right, but maybe more than we need to do for this question, and we do want to be a little bit about efficiency, let's just calculate a probability. So basically the way that would go is this. You know that, just like we were saying, the probability of any one of these particular outcomes, and we listed out 8 of them, would be 1/8, right? In other words, we know that if we guess 3 particular outcomes, we have to get, if we say tail, heads, heads, then for us to lose all 3, we have to get heads, tails, tails, right? And that is only one possibility out of the 8. What that means for us here is, however many trials we have, we'd have to take 1/2 to the power of that many trials. So if it's 4 trials, there'd be 16 ways it could go. The probability would be 1/16 of us getting one of those one particular outcome out of those 16 outcomes, right? And we have to get that one particular outcome for us to fail every single time, for us to have a p hat of 0. That's what has to happen. So this is the probability of all being losses based on n trials. Okay, so what we want to know is, when is this less than our significance? And our significance is 0.01, right? But we'll make the, you know what, we'll just make the test even more powerful. I mean, why not? Let's say it has to be less than 0.005, just to be really safe. Okay, well, there's a couple ways we can go about this, because the question all it wants to know is, what is n, right? How many trials? In how many trials would this happen? You can just start listing out, what are the powers of 1/2? And at what point do we get a power that is less than 0.005? Well, if you really know your decimals here, you might just know. Or you might, plug in, and you would see that 1 over 128 is equal to approximately 0.0078, which is still too much for us. So we go to the next one, which is the 8th power of 1/2, and we get 0.0039, and now we're really cleared, and now we can really reject the null hypothesis. So in other words, if he can call it 8 times in a row, that is getting very unusual. Okay, not call it, but somehow make you lose 8 times in a row if he claims that that's what he's doing. Okay, so at that point, maybe you can suspect that your friend is doing something. And by the way, you might recall from algebra how to solve this equation directly. You take the log base 1/2 of 0.005, and you'd get 7.64, which, according to this, has to be less than the number of trials. Therefore, the number of trials is at least 8 to achieve a power of 1/2 that is less than 0.005. And that is 7D. All right, so moving on now. Yes, we are rolling. Okay, moving on to, this is number 23 in chapter 21. Okay, so this is about the basketball player, and we want to know if he's improved, so I won't read the whole thing. Okay, so A, suppose the player really is no better than before, so suppose the null hypothesis is true. He's still a 60% shooter, so this is the null hypothesis, that this is the actual percentage. What's the probability you could hit at least 9 out of 10 shots anyway? Okay, so this actually doesn't take too long to calculate the exact value. We just need to say, okay, we're looking for the probability that x is greater than or equal to 9, given that probability is 0.6 and n is 10. So for a binomial variable with p equal to 0.6 and n equal to 10, what's the probability that x is 9 or 10, right? If x is greater than or equal to 9, the only thing greater than 9 that it could be is 10. So this is going to equal the probability that x is 9 plus the probability that x is 10, right? We just have to calculate them separately and add them together. So this is going to be 10 choose 9 times 0.6 to the 9th power times 0.4 to the 1st power plus 10 choose 10, which is 1, of course. So this is getting back to the business in chapter 17. Okay, so binomial, and we bang this out and we get, I think, this, or something very close to it. So here's what that means. If we assume the null hypothesis is true, I can do a little better than that. Okay. I'm not really good at drawing with this, am I? But whatever. So we assume null hypothesis is true, so the center is 0.6. That means that 0.9, which is at here, this would be the actual region where we would have alpha equal to 0.464, right? In other words, the probability that I get beyond this is 0.0464. Now, there's something I'm about to get to that makes this, what I'm saying, not entirely true, but for now it's fine. So in part B of the question, it says, if that happened, right, now the coach thinks the player is improved when in fact he did not. So what type of error is that? So you should remember by now that is a type 1 error because we rejected the null hypothesis. We rejected that he never got any better. We say that he did get better because the evidence overwhelmed us when in fact he did not. That is type 1. Okay, so this is the probability that we will think that the player got better when in fact he did not. Okay, now the next part, C, is very tricky. So this actually had me stumped for a while. It says, what if the player is improved and his new value of P is 0.8. So that's like right here. So let's say that's the actual center of the distribution, right? Is 0.8. Okay. Now, that means that our P star here, 0.9, is cutting through both distributions, right? So, this is the probability of a type 1 error right here. So the probability of a type 2 error is all this, and it's a huge chance, right, that we're going to have definitely more than a 50% chance we're going to make a type 2 error with this test if, in fact, his value of P, and this is what it depends on, if his value of P is actually 0.8, then there's all this chance that we would that we would not reject the null hypothesis when in fact we needed to because he had actually improved. So we wouldn't be giving this player the credit that he deserved, right? So just think about how that would happen. Let's say we assume he has 0.6 when in fact he has 0.8, and he shoots a little, in fact, let's say he shoots 0.8 exactly. Which is exact, he gets exactly 8 out of 10 shots, which is exactly his new p-value. Well, that wouldn't be enough to convince us. We wouldn't reject the null hypothesis. We would say he was still probably at 0.6, when in fact he deserved to be recognized. Now, of course, this test and this test has such a bad, we'll say a low power, because it's only 10 free throws, right? It's of course unlikely that he can really prove himself in so few free throws. But when we talk about the power of the test, literally we're talking about this. So the power is the rest of this, which equals 1 minus beta. So beta, this is alpha, area over here, probability of a type 1. This is beta, area over here, probability of a type 2, and then the power, is the rest of this distribution. It's 1 minus beta. Now, here's where this gets tricky, because I calculated what this would be. I went ahead and did the standard deviation, and I said, okay, well, standard deviation of this distribution is going to be 0.8 times 0.2 over 10, because that's the sample size, and we take a square root, and then I figured out this is 0.1 away, right? 0.9 minus 0.8 is 0.1. Divided by standard deviation, got a z-score, looked it up in the table, but then what the table was giving me and what the answer in the back of the book said did not agree. So I had to sort this out. So here's what I sorted out. This is not a continuous distribution. I'm drawing this as though P could not only be 0.8 or 0.9, but it could be like 0.85 or 0.87 or 0.8815 or something like that. It can't take on those values. We only have 10 free throws here. P can only be 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, or 1. Those are the only possible values for P, and those are the only possible values for P hat. Well, no, I shouldn't say only possible values for P. Those are the only possible values for P hat if we're only taking 10 shots, right? If that's what we're sampling from. Okay, so if that's all that's possible, here's what I really need to do. I need to say, look, if we are going to reject the null hypothesis, if he gets 9 out of 10 or 10 out of 10, in which case we'd have 1.0 here. If it's this or this to reject, right, that means that the power of the test would be the same thing here. In other words, beta, the actual value of beta, would be the probability that x is less than 9. In other words, that we get fewer than 9 successful free throws, given that the probability is actually 0.8, right? So in other words, what's the probability that we get exactly 0, plus the probability that we get exactly 1, plus the probability we get exactly 2, on and on up to 8, plus that probability as well. All that will be beta. That means that the power actually, since it is 1 minus beta, will equal the probability that x is greater than equal to 9, given that p equals 0.8. So the same thing we did right here, where we're assuming p is 0.6, and we added the probabilities of x being 9 and the probabilities of x being 10. We have to do the same thing here, assuming p is 0.8, to get the power of this test. So, okay, so let's do that. Okay, so yeah, this is a little complex, but this is important to point out. You know, a discrete situation really is different from a continuous situation, and you'll find that the probability we get here is quite different from what I would have gotten if I had done this, which is not what I want to do, right? I don't want to do that in this case. Okay, so we want to do same thing we did here. We want to do 10 choose 9 times 0.8 to the 9th times 0.2 plus 10 choose 10, which I know is 1, times 0.8 to the 10th power. And that comes out to, what did I get? 0.376 if I round to the thousandth place. And that is what it says in the back of the book. Now, if I go with this other method, I get something way less. I mean, it is way off. It's not just a little bit off. So I really do need to take this as a discrete situation, calculate probability, because, okay, and once again, let me just say what we did. The problem says we're going to reject the null hypothesis if our player gets 9 out of 10 shots or 10 out of 10 shots, we reject the null hypothesis. So since the power of the test is the rest of the story here, that's what we have. Okay, let me say it again. We reject the null hypothesis if the player gets 9 out of 10 or 10 out of 10. That means that we don't reject in any other case. So beta has to equal all of that probability. On this other distribution, it has to be what is the probability that given that the player actually has this improved chance of scoring, improved chance of making a basket, what's the probability that the player makes 0, 1, 2, 3, 4, 5, 6, 7, or 8 out of the 10? Because in any of those cases, we will not have rejected the null hypothesis. So all that was our beta, and therefore the power is what's left, which is the probability of 9 shots out of 10 or 10 shots out of 10. And that's what we have to do to calculate the power. Now, for D, it says, list 2 ways the coach and player could increase the power to detect any improvement. So it says this in the back of the book, but basically, if we want to make the power greater, in other words, if we want this area to be more than what we see here, well, then we have to lower this bar, right? What if we took P star, instead of saying we'll take 9 out of 10 or 10 out of 10, why don't we take 8 out of 10, right? And then the bar would be right here, and then all this would be the power of the test. So that would be more. And the other way to do it is to change the standard deviation, and you do that by increasing the number of shots that the player takes. So increase the sample size, and that's going to make our distribution look more like this. Whoa! Hold on. That's going to make our distribution look more like this. And then if we wanted to do, you know, say a significance level that was like this, then we could go all the way out to here. And then if we increase this to, you know, so that in that way you could have like a huge, like, you know, a much, much greater power of the test. Okay. Moving on to number 23 in chapter 22. I've been warned about this one. Okay, now, as it turns out, this one is not too bad, actually. I think that the basketball example was actually a little bit trickier than this one. So, all right. So first we write a 95% confidence interval for the medication A people. So this is 84 people felt better out of 112. That's actually exactly 75%. So if we want confidence interval, we need margin of error, which is going to be, for 95%, it's going to be 1.96, I don't know if you remember that, times the standard error, right? And the standard error equals p hat times q hat over n, all under the radical. So in our case, that is going to be 0.041, and we multiply that by 1.96, so we get our p hat of 0.75 plus or minus 0.08, and I think you get something, I'm going to get something maybe very slightly off from the back of the book, but that's okay. So this takes us from 0.67 to 0.83 with 0.75 in the middle. Okay, then the other, that was for A. For B, we had, what, 66 out of 108, so it's the same story. We're going to do this. So to get standard error, we're going to do 0.61 times 0.39 over 108 under the radical. So you get, I think you get this. And again, I think I rounded differently from the book, but I have 0.61 plus or minus 0.092. So that takes me from like here, this is not going to be to scale, but 0.518 to, and I'll do this one in, let's say in highlighter, if it'll let me. Okay, up to 0.702, so that's like up to here. Yeah. Come on now. 0.702. Okay. So this is interesting. Part C says, do the intervals overlap? Of course they do. What do you think this means about the comparative effectiveness of these medications? So at this point you might say, well, look, and I didn't say what these mean. I didn't say out loud for parts A and B. So let's say what this means. In part A, I am 95% confident, right, that the actual effectiveness of this medication is, this medication will make between 67% and 83% of the population feel better, and I'm 95% confident that this medication will make between this proportion and this proportion of the population feel better. So the fact that they overlap means that, well, maybe the actual p-value for A is in here, and maybe the actual p-value for B is in here, and they might actually be the same. In fact, these two medications, there might not be any difference between them. So here's what we have to do. We got to do we got to basically subtract them and make the confidence interval that way. So we got to do confidence interval comparing the two, right? So the difference in the proportions. Okay, so we did a bunch of these before. So we have p hat for A minus p hat for B is going to equal, 0.14 approximately. And then to do the margin of error, for the standard error, we're going to have to do we're going to have to do this business, right? Where we, under the radical, we add what are essentially the variances, although they're technically not variances. But this is our p hat for A, and this is our p hat for B, and this is our n for A, this is our n for B. So basically everything we did here is here, this radicand is here, but we add them before we take the square root. And we get, well, I didn't write down what I got. I just went ahead and multiplied that by 1.96. I got the margin of error, and that was 0.122. So, all right, so that means our confidence interval is 0.14 plus or minus 0.122, which is going to be, let's see, what do I have? And this is where I think I got maybe 100th or two off from the answers in the back of the book. Okay, so it's about, it's like from here to here. Okay, so let's think about that. We're 95% confident that the true difference between the effectiveness of these two drugs is between this number and this number. Well, that changes things quite a bit, doesn't it? When we're looking at this picture, it really looks like there could be no difference, right? But now we're saying that we're 95% confident that the difference is between almost 2% and 26%. And certainly then, we are more than 95% confident that the difference is greater than 0, right? That there is a difference at all. So we are quite confident that there's a difference. And we're much more, in our minds, much more confident now than we were when we were looking at this, right? So, and part E is, does the interval contain 0? No, the interval does not contain 0, right? That's the point. So part F says, why are these parts contradicting each other? If we're so sure here, why were we not so sure when we were looking here? Why did it seem like there was the possibility? Well, what they explain in the back of the book is that the fact that we're adding what are essentially the variances here is the key to why this test is the appropriate test. If you want to know if there's really a difference, right, you got to subtract the proportions, and therefore you have to get a measure of spread that is appropriate for that statistic. And the fact that we are going to have a different variability, right, is what makes us even more sure. And there you have it. Okay. So once again, confidence intervals individually, we're fine for talking about these individually, but if we want to compare them, we do need to do this. And that's also a good argument for why we subtract proportions when we're comparing populations in a hypothesis test.